Welcome everybody again to another exciting ROMER talk. Today our guest is Dr. Alp Karacakol from Max Planck Institute. He was a student in electrical engineering department in METÜ. Later he moved to Carnegie Mellon University and he did his PhD jointly with Max Planck Institute. After that he stayed in Max Planck, this time did his postdoc jointly with ETH in CLS program. And now he's a co-founder of a microrobotics startup, Cell and Roll, in Max Planck Institute. It's my pleasure to give stage to Dr. Alp.
Thanks, Efe. Thanks for the invitation. It feels good to be back at METÜ for a talk. Is my voice good, by the way? All good? Okay, perfect. So today's talk will be mostly from my PhD and postdoc work, but I will also mention briefly about what we do at Cell and Roll. And there is a bunch of logos. We will come to that later. So if I already mentioned, I was at METÜ and then Carnegie Mellon and then Max Planck Institute for my PhD. And along the way, we made a bunch of good friends. Basically, 2016, graduation from METÜ, 2018, my master's from Carnegie Mellon, and 2022, did the PhD graduation in Germany at Max Planck Institute. And there's always this hat tradition where they make hats with all the memories on top of you, like your friends make it. And Efe was actually one of the best ones who makes these hats back in the days. So after that, I started the postdoc fellowship at the Max Planck ETH Center for Center of Learning Systems. And that was about a year and a half. And since exactly a year, actually, we are trying to start a startup called Cell and Roll. It's still at the pre-startup phase, but we are getting there bit by bit. And today's outline will be just like 5 minutes introduction to the magnetic soft robots, or like magnetic robots in general, and then 10 minutes mostly on the magnetic programming, what it is, and about 20 minutes more in depth for the data-driven design of magnetic soft robots. I thought it will be a more fitting topic for this talk. Afterwards, briefly about all the simulation works we developed over the time. And at the end, a glimpse of what's next at the Cell and Roll, what we are doing and what we are trying to achieve. So start with like our PhD lab was called the Physical Intelligence Lab. And it was a crowded group. It's right now closing down because Professor Metin Sitli moved to Koç as a rector. And that was the group at the time. It was about like 6 to 8 people, depending on the season and the collaborators and the visitors. But the lab's goal was basically trying to develop medical robots. And when you think about the medical robots, it needs to be most of the time small because their idea was to use it in, like the lab's idea was to use it within the human body. During my PhD and postdoc, I mostly focused on these two parts, but the lab was huge. Everyone was focusing on different parts. But today's talk will be mostly on these two, design, manufacturing part, and also the actuation methods for magnetic soft robots. To move on, when you think about like the actuation methods at the smaller scales, there is like a wide variety of choices, but our lab was mostly focused on the magnetic because basically it's the best choice for the untethered actuation, and also it has like a safe penetration through biological tissue, and also you can achieve fast response times because you can change the magnetic fields, external fields, quite fast. And some of the methods are relatively slower, etc. That's why the main focus was on magnetic robots. And it got to be small. So how small? That's a general question we get. So it's actually 2 parts. One part is the micro robots, smaller than 100 micron level. And the other part is milli robots, which is basically the other side, bigger than 100 micron, like millimeters sizes, like 5-10 millimeter range. And this is like basically most of the time at this scale, we have these magnetic soft robots. Just like a 101 for magnetic soft robots, basically just to simplify, let's assume there's a fixed surface and there's a rod. And this rod is made of a polymer matrix and magnetic particles inside, embedded inside. And by alignment of these magnetic particles, you have a certain magnetization direction. Just a second, I want to restart the timer so I know how long I have. So basically, depending on this magnetization alignment, you can apply a certain magnetic field, external magnetic field, and create this rod shape utilizing magnetic torque. And the why I only talk about magnetic torque is because we most of the time utilize uniform fields, try to avoid gradient forces. So it's only the torque that's applied on this robots. So basically, to wrap up, there are three main things: the magnetic programming of these robots, the structural design, what will be how tall it will be, or what will be the material type, etc. And then lastly, what will be the applied magnetic field. And this part is mostly on the control side. When we think about the magnetic soft robots, like just a brief overview, this is like kind of outdated, of course, because this is left from my beginning of my PhD times. What has been shown was that you can make small scale grippers for object manipulation. And you can achieve multimodal locomotion, where you can achieve like jumping, walking, crawling, and all sorts of different motions. And I think up to 10 or 11 different locomotion modes. And also, more interesting part is also like for the biomedical applications, you can achieve locomotion within enclosed areas. Like this is like a blood vessel model. And there's a laser at the tip of this robot sitting somewhere here. Yeah, to for example, burn an area. So back to the challenges. I'd already mentioned the magnetic programming. There is one challenge there for the fabrication part. How do we make the alignment of these particles within the polymer matrix? The next part is design. What will be the structural design, but also how you will program these magnetic alignments will change the whole response of the whole robot. And that's also another challenge. After that, also the magnetic fields, you need to apply the control challenge. And lastly, the simulation part, because since it's soft-bodied structures, it's really hard to simulate these things. And due to physics, non-linearities, etc. I will move on to the magnetic programming. Basically, in my talk, it will be mostly focused on the magnetic programming, the design challenges, and the simulation frameworks. The control part was not my part during my PhD, but it was actually another alumni from our lab was working on the control part during my time. So for the magnetic programming, brief history, there are like main methods back in the time when I started. The one part is the particle patterns, which means when you embed these particles inside the soft body, before you cure the polymer, you try to align them in the direction you desire, and then cure the polymer matrix, and these particles embedded inside in the direction you want. That's the one method. And basically, you can create 3D structures or utilize 3D printing with it. Another one was we called template-based, which is simply you basically fabricate these soft elastomers and then apply saturating magnetic field program while keeping the shape you want to achieve with these robots. And lastly, which is a bit more harder to do, like it's the most expensive way to do is, I guess, create the single domain nanomagnets at the really small scales, where by basically creating the single magnetic domains at these structures at different lengths and widths, you can change the magnetic properties. And this is like for creating really at the small scale robots. So every one of them actually was trying to address one methods in these area. And it's a bit complicated because it's hard to get a grasp of what's happening in the field. So we kind of created this chart to show, in general, every method was just trying to solve one problem, but none of them was able to actually really solve several problems at a time. So we were thinking, okay, how can we find a method where we can target all? And for this, we proposed the heat-tested magnetic programming, inspired from actually heat-tested magnetic recording technology in hard disks or cassette tapes. The idea is basically after you fabricate your elastomer, you apply a heating to the desired location where you want to program, and you heat it till the cure temperature. when you do this, the domains becomes like the basic magnetic property becomes paramagnetic. Then you can apply external field, not a saturating field, but like as low as 10 millitesla to align these domains within the heated region. And when you cool it down while applying the field, after the cooling down phase, basically that region of interest is programmed in the direction you want. By this way, you can program every small bits of this soft elastomer in the direction you want. That means the response will change accordingly. Just a simple quick showcase so that it's easier to understand. So let's say we are trying to make a cube and we have these 6-phase cube design, and we have these arrow directions for the magnetic programming. What we do is for our setup, we have the sample part, we have the magnet, and we have the laser. We hit the desired region and then basically move on to the next part, and it goes on, and we automatically program every bit of this structure. And after that, we can measure it using a magnet optical device. It's a bit hard to understand, but I will show a bunch of these, just like simple way. You just try to measure out of plane magnetic field strengths with this device. And at the end, although you can clearly measure the out of planes, for in-plane mine stations, you get something like this, where you can see the ends, but still it's a clear indication that we can program these material in the way we want by measuring this device. And at the end, when you apply the magnetic field, just a simple quadratic magnetic field, you can achieve the shape you want. So on top of this, although like we have now a good fabrication method, we want to also develop simulation model on it. So we basically used back then just COMSOL, like a FEM-based tool to simulate these behaviors and to make our design process easier. And basically the model was validated and it was quite good. And at the end, it was kind of the full image where we can fabricate the design we want, and we can iterate our designs in the simulation model beforehand. So no need to do a lot of trial and error process. Then we basically try to push the limits of this method because we know, okay, we can potentially magnetize it in any direction. So we were able to magnetize these particles at 3D direction at any point we want within these soft elastomers. And all these kind of just like validation demos. And the good part is, the good part is when you can just heat it up a certain region, desired region, and change the magnetization programming, that means you can actually reprogram these materials at the time you want. So that brings the reprogrammability into the game. And basically for a simple like a demo like this, where normally the motion is like in a circular way, you can basically by changing the magnetic programming of certain parts, you can achieve a different locomotion mode. The next part was the desired thing, because as you can program these things at a smaller scale, that means you can achieve more complex behaviors out of these elastomers. So we were trying to go as high resolution as possible. And for this, one thing is, yeah, okay, we are using a laser, you can make the laser beam smaller, easy. The second part is by using this, we were able to achieve like down to 100, 150 micron. After that, we were not, you need to create a kind of a more sophisticated optical setup. We did not get into that. We were looking for simpler ways. The next thing is basically you can just use a photomask in the shape you want. By shining the laser through it, you can basically create the pattern you want on top of the surface. And we were able to generate like these MPI ladders from Max Planck Institute. I think here, like scale is like around 100 micron again. But where we did the highest resolution was basically contact magnetic transfer, because you can generate simple primary magnets with the desired magnetization programming as a master, like a primary method. And you can globally hit the whole thing while this is on top of your elastomer is on top of this primary sample. When you cool it down, it's actually fabricated, basically programmed in the way you want. And by using this, we were able to go down to 25 or 37 micron, actually, exact 37, I think, micron. Or 36, yeah, sorry, 38. Yeah, anyways, around 40. And we were able to achieve this really complex pattern actually at these resolutions. And this kind of brought us, like showed us that our method was able to generate kind of target all these problems, at least most of them in the area, one by one. And like we were only kind of, okay, we cannot generate directly 3D structures, but there is a way to do this. I did not show it, but also the resolution is as low as the single domain nanomagnets. So overall, it was kind of a really good method. And it kind of actually also was the base of my whole PhD, because I used this method during my whole PhD time. I will not go into the details. I'm a bit running slow. I'm doing it a bit slow. So at the end, for the method, we have a pending patent, and also this work was published in the Science Advances, which you can read for like through the Eduram now. I saw it, because apparently, yeah. Anyways, and in this paper, like my collaborators were Yunus and also 2 interns, Iran and Sheyda. They did also an amazing job. That's why we included them in the paper. And moving on to the more, I think, fitting structure, like fitting topic, the data-driven design of these magnetic soft robots. So I already showed you different fabrication methods, like different magnetic programming methods. And what's happening in the field is more and more advancements in the fabrication techniques. Every year, at least 3-5 papers are published, which is like pushing the boundaries of these fabrication methods. And also new, like not only magnetic particles, but the direction is also towards the multi-material structures, which means you include other responsive materials like thermal, etc., into the body of these robots. So the complex design space you can achieve is increasing rapidly. But when you check the papers and all the designs in the literature, most of the complexity is kind of already stalled for the last 5-10 years. There is not much on the magnetic soft robots field, at least. Designs are relatively simple. So this was kind of interesting, and our idea was, okay, this is because simulation tools are really slow. You cannot do a lot of iterations in the simulation part. Physics are super non-intuitive. We cannot generate these designs by like intuition. It's harder. And also, when you try to do it in that way, just relying on your intuition and do a lot of trial errors, it's so non-intuitive. It takes forever to make one design get to work. And this is also why I think people simplify all these designs to a point where they can manage doing the intuition-based designs or bio-inspired designs. So that's why we want to target this. And when we look at the design of the magnetic soft robots, I already mentioned that the easiest way to deal with this complexity is to simplify, which means most of the works were keeping one part predefined. For example, keeping the structure will design predefined, just a certain shape, but only work with the magnetic programming of the sample, like the robot. Or simplify, like involve the structural design at the one-dimensional way, which is just like changing the length or the width of it, but also simplify the magnetic programming to one dimension, or like just involve the structural design, but simplify the magnetic programming. So we were interested in, and these are the examples, basically simple shapes achieved by these broad structures. And our idea was like, why don't we try to push towards like the most complex structural design and the magnetic programming? And we know for the fabrication part, we have a really good method. So the challenge comes from actually it's super coupled, because you need to think about the control field, the magnetic programming methods, like the programming within the material, and also the overall structural design. So just take this design granted for now. I just want to show you some simple demonstration how complex it may get. So for this design, where there is like a certain structural design and there's a bunch of magnetic programming methods at smaller scale, it's not important what's this, but the overall message is when you try to change something as small as like 30 degrees here, like just one of the magnetic programs here. Sorry, by the way. You can see, right? Okay, perfect. The overall shape change becomes drastically different. Like, so this is actually equivalent of a 0.4% change in the overall design for the magnetic programming, but the end result is drastically different. And the same thing for the morphology. If we just cut, this is like a 12 millimeter long sample. If you cut 200 micron from the tip, you have drastically different shape again. And this was interesting already, and then we kind of did a bit more in depth to this. sensitivity heat map to see, is it really as nonlinear as we think? And we basically created these segments and then the relative angles, and then we simply, for each segment, we changed the relative angle and just try to see how nonlinear it is. And you can clearly see it's like there are some parts, like certain segments, there is nothing changing. There are certain segments where there's a drastic change, and also there are weird jumps as well in between. And this was already like clear. Okay, we as we guessed, the nonlinearity is there because of all these coupled interactions between the mechanical forces, magnetic forces, and everything. And it was just like in the field, people did not believe us. We just want to show it this way. And then when you check all these different cases, you can see how hard, if you want to kind of do it by hand, like by your just relying on your intuition, and just a slight change ends up drastically different. That's why we said, okay, we should target this using a data-driven design method. And for this part, we want to simplify, because our idea was like the design part is so immense, like so vast, design space is so vast. We can simplify the control part just to like a predefined magnetic field. We simplified that part, but the idea was to focus only on the design part. And we either define a certain behavior, like it could be a jumping, like a robotic behavior, or just simple shape morphing for comparison cases. And the idea is with the open algorithm, and it gives us the magnetic profile or magnetic programming of the robot, and also the robot morphology, meaning the structural design of the robot. And for this, we utilize Mapellets as the main algorithm, which is a heuristic algorithm, similar to like kind of a modern genetic algorithm at the end. And we combine this with a surrogate model. And I will show you a bit more details on this part. And then we basically combine with a simulation to run all these different demonstrations, which relied on a mass spring lattice model. And that was the main algorithm. And for the representation of the design space for the magnetic programming, we used the segments and we directly encoded it. But for the robot design part, we used these compositional pattern processing networks. This is a neural architectural search network, quite old, but it was shown quite useful for generating different soft robot morphologies, like structural designs. That's why we used this to simplify that part for the parameter numbers. And when we, what algorithm does is basically it generates a certain design repertoire, and among these we like get the best design, and this best design we fabricate it and we show it in the experimental results in experiments. So for the algorithm, what we did is I told you the Mapellets. It's not super important what is in there, but basically it's kind of a genetic algorithm, evolutionary algorithm. But this part is only responsible from the design alterations within this design space. After it generates a 250 designs, it asks to the surrogate model which ones are the best to try in the simulation. And then 50 of them are sent to the simulation. And then simulation results updates the data set, and then also the archive of the Mapellets. And basically this iterates over 5,000 generation. We limit it to 5,000 because over time we realized like this is like sometimes takes about 3 to 5 days. 3 to 5 days to run these things in our cluster environment, because the simulation model, although it's efficient, still relatively slow compared to other simulation models. And basically, over time, it's kind of a virtuous cycle here. As the dataset gets better, the surrogate model gets better. So that your predictions for these designs gets better. That means you choose the better ones to run on the simulation. And as you run the simulation on the better designs, your dataset gets better, and then just kind of both hands gets better and better, and then you achieve kind of a better performing designs at your archive over the time. And why we did not just train a bunch of generate like bunch of data and then just run it train it on the circuit model and use that as a simulation environment. It's because design space is huge. It's like enormous. It's like for simple cases 10 to the 100s, 10 to the 500s. We were not able to generate enough data to make a surrogate model which is good enough to predict everything. So basically, for specific design, we trained it online over the time during these iterations. For the simulation part, I already mentioned we did come up with this COMSOL model, the FEM-based one. Also in the literature, there were other models, but they are quite relatively slow. That's why we were looking for something faster. There is no way we could run 5,000 iterations with these simulations because some of them takes like an hour, 2 hours even. So we were looking for open source models. What's available? There was SOFA, there was Voxelize, Chain Queen, and Titan. By the time we look at this was like, I think 2020 or so. And we chose the Voxelize as the best because these ones were at their early steps. I think right now Chain Queen V2 is really good. Check it out if you're interested. But back then Voxelize was the best. And it was kind of, it had all the features we were looking for, which means it was able to like do dynamic simulations. It was relatively faster, like from hours to minutes. It was able to handle the contact forces so that we can do actually untethered robots simulations. And from the name, as you can understand, all the structures are represented by the voxels. That means you have a generic representation method, so you can kind of create any kind of shape you want in 2D or 3D by changing the voxel sizes. And also, it was able to deal with the multi-material structures or like heterogeneous materials. That's why we took that, put the magnetic forces and torques into this simulation, and it was actually working as good as our FEM simulation, which was like really good for us. And we basically validated, and also we tested the time run of this simulation actually because it's crucial for deciding how long we will run this algorithm run in the for getting the best design. So we find, depending on the voxel number or for our region of interest, we were able to run it within 1 to 10 minutes or 1 second dynamic simulation, which was good enough for us. And then we moved on to different demonstrations. Basically, we started simple. We started with tethered samples because it's easier to compare the error, like for compared to simulation, experiment, everything, because you have 1 point fixed. So it's easy to kind of measure the exact shape error within these samples. Here, it's just like the one of the first demos actually we had. Basically, the desired shape is just like this kind of a zigzag shape, and the morphology, the algorithm generated is here, and this is the design with the magnetic programming on top of it, and then we're able to show it in a simulation and experiment, and you can see all the side top front view and also on the experiment side here. Then we also showed it for 3D shape morphing of the samples, which means shape morphing within 3D space. Here we try to push the boundaries by making these sharp ends, because with a soft body it's actually quite hard to achieve such things. So we basically try to push the boundaries of this algorithm, and the result was quite good. Although there's like with the 3D shape morphing, the simulation to experiment transfer suffers a bit, but I think that's okay because we never actually validated for the 3D shape morphing for 3D shape morphing for the developed simulation model. And then we basically went crazy, tried a bunch of different demos to see, like try to push all the boundaries inspired from different mathematical functions, and or just truly like just curious if we can generate such sharp corners here and here. But this was just a start, because this was just to see if our method works good enough, and we put on top of it and want to go towards robotic behaviors. But we started again simple. We tried different morphological behaviors. What I mean is just like maximize the turn number around your body, or maximize your central point, or minimize the enclosing volume for your structure. And after this, we were convinced that we can go towards the robotics, but we also want to compare it with something, because it's a bit harder to compare. When you move to the robotics, there is not good benchmark. So we were looking for any example in the literature where everything is well characterized. And we found one from our lab actually for jumping behavior. That's why we started with that. And basically this design is the intuitive design. adapted from our lab's work from 2018. And the difference is, though, design is the same, but our material, due to our magnetic programming methods, is 1/3 of the material actually they utilize in this paper. That means all the magnetic torques for the same magnetic field, it means torques are 1/3 of this paper. And we're curious, okay, if under these conditions, would it jump? And what we found is it didn't even like move even a bit, no jumping at all. And we were like, okay, cool. Let's see if our algorithm can find a jumping behavior under this condition where other design failed. And for this 2D structure, we run the algorithm, and actually it finds something quite good. And it is even actually for the body length, when you compare the body length jump height, it's actually even higher for the other paper, compared to other paper, for the same magnetic field. And also in this paper, it was mentioned as the aspect ratio gets closer to 1, it's harder to jump. So we were just curious, can we also do it with the kind of a sheet shape structure? And you can see it's like 25 times slower, by the way. It was able to lift off even under this condition. And since the algorithm was structured in a way where we can parameterize it using these CPPNs, compositional pattern networks, you are able to also extend to 3D structures and also multi-materials. That means we can involve suddenly like a bigger design space into the art game. And for this, we involve passive elements like rigid and soft structures to the material palette, and also magnetically responsive materials, but one is soft, one is rigid. That means it can induce rigid parts within the body or soft parts. So it's kind of a hybrid body. We fabricated using a different method, of course. We just want to show the extension of this method and capability of this method. And the basic thing is basically you just combine these voxels to each other with glue, kind of a thing. Like tedious, but simple to do. And takes time. That's why we try to simplify it by making the voxel sizes way bigger. So like compared to previous experiments, these are actually way bigger robots. Like the size are almost 1 to 2 centimeter. Before it was like below, mostly below 1 centimeter. So again, we want to show, okay, we did like a horizontal jumping, let's try directional jumping. And it was able to find designs which is able to generate, again, combining these soft and rigid parts within the body, jump directionally in like X direction. And also we try to come up with this traversing, which is kind of like locomoting without liftoff, like no jumping basically in the body, basically trying to create steps. And I think the one thing is actually it was trying to create these like 2 limbs, but the resolution is low, so it was able to generate only this at the end. And I'm running a bit late, so I will just move on really quickly. Basically, you can also combine different stimuli responsive materials into this algorithm as well. And then you can, for example, change the behavior depending on if it's heated up or cooled down for the body. Then it means it can walk or jump, for example. So sum up, we were able to actually involve the whole 3D programming space and also the 3D structure space in this work. And when we checked, like we want to look a bit also broader, because we notice also like it's a common problem in all this stimuli responsive soft robots field, which means all these thermal responsive and electronic responsive, etc. They have also similar problems, and we want to compare also with them. It's not a perfect comparison, but it's like still represents something. And we notice actually we also kind of compare really well compared to all other these stimuli responsive soft robotics fields where they develop different design methods. And this paper was like, this work was super interdisciplinary when you think about it, and that's why also it finds its space. It finds it's got like a contribution to different places. One was I was able to present this at the Neural Information Processing Systems, the preliminary version of it at 2020 at the Machine Learning for Engineering workshop, and then I was able to present at the Material Resource Society conference, MRS Fall in 2023, and also at the robotics GRC robotics conference in 2024. And also the paper is finally out this year, like just I think 2 months ago, at the Nature Communications. And on top of that, we generated so much data, like I think it's 35 million. It's the first time I think in this field such a thing is done. So we also open shared all this data set to the with the basically with the people, other labs through the Zenado, and also all the code and algorithm simulation, everything is available also in the Zenado. So we open shared everything to see if people use it and then make something better out of it. And the last part from my PhD and postdoc time is the simulation frameworks. I already showed you different simulation frameworks so far, but during this previous work for data-driven design, we noticed still the bottleneck is actually simulation. If you can achieve faster simulation times, you can actually push way push the boundaries even deeper or more. And that's why we were kind of checking different papers here and there, and we found actually collaborators from UCLA, from Los Angeles. It's a structural mechanical group, and they are focused on basically soft robot simulations. And in the literature, I will show you quickly that we have our own works here and here. And then there are also other works in the literature already. But the problem is either it takes so much time, it's quite static, or again, it's quite aesthetic and capabilities are limited to 2D mostly. And the fast ones are super limited, like 2D, quastatic, no dynamic simulation, and the shape is super simple and so on. So that's why we want to create a new simulation environment which will run way faster. And this is unpublished work, by the way. It's about to be submitted. We do it right now in our free time with our collaborator. This is Sangbin and this is Professor Khalid. And basically, they are experts in the modeling for soft structures and soft bodies. And we try to generate a model where we can achieve like kind of simulate the bending, twisting, and all these things in the magnetic soft robots. And what we did is actually they were expert. They already had a nice paper on combining discrete elastic rods model, which is highly used in like computer vision people where when they try to simulate, animate soft structures. And we combined that with the magnetic forces and torques. And we were able to achieve quite a fast simulation tool through this. And after fixing so that you have like certain number of nodes, and you need to find a certain node where it's converged, certain number of nodes per length within the body. After it converges, you fix the number, and then we checked it, and we're able to show if the time step is below 5 milliseconds, higher than 5 milliseconds, we were able to achieve faster than real time. And although like till here, it's still faster than any other simulation model we have seen. So even the running it at the smaller time steps is faster than the other ones. And I will not show too much. One validation case in 3D, we kind of create a really like complex control field where the field is moving around, and we were able to quantify it quantitatively and qualitatively for this rod shape. And on top of that, we actually tested under diverse conditions, like different magnetization profiles, like discrete or continuous, different structural parameters, length, width, etc., different environments like air, glycerol, water, different material types, like different polymers, different ratios, different magnetic particles. And also for the control part, control signal, the magnetic field part, circular, elliptical fields, or different frequencies. We tested all these, but I will only show one specific demo from these, which is like, which was surprising to us. We did not expect this. When we saw that we were able to capture the buckling, which happens in like, I think it was like 20 milliseconds or something. We were impressed. And I will just show a quick video. Here, like it turns one time, and then base energy builds up, and then there's this sudden buckling movement, like a WIMP. And we were able to achieve this, and I don't think I can achieve it, for example, if I try with the previous model, which relies on the mass spring lattice model. And then we want to extend it towards untethered robots, where by combining the contact forces, by combining the contact forces, we want to show the untethered robots at the end. Like for tethered ones, the main application is catheters, etc. For the real application on the biomedical side, but the untethered robots is also another direction people try to go. So we want to also show that, and basically show the walking, like commonly used ones like rolling and jumping within the simulation as well, which extended the capability of this developed framework. And to sum up, like this model compared to rest, we are able to achieve the dynamic simulation. It is capable for 3D shape morphing within the space, and also we can achieve like seconds or below seconds, almost fast times, as fast as real time. And basically we will submit it soon. So overall, during my PhD and postdoc time, I did work on magnetic programming methods and the data-driven design part of these robots, and then the simulation part, which is kind of, I also worked along the way in also other simulations, sorry, in other projects as well. And this was kind of my PhD, and then a bit of my postdoc time in the this design part, the last bits of the multi-material, etc., extension into that part. Was during my postdoc time. And also during this time, I also contributed to other works here and there for different magnetic microbot papers, and also ferrofluid, magnetic ferrofluid robots. And I think, yeah, this was it. And I need to acknowledge all these funding sources at sort of different times, which funded me. That's like kind of wraps up all my like kind of research career so far. And now what's next at the Cell and Roll? So this is kind of new. Like I'm 100% on this now since like last May. Yeah, so it has been exactly 1 year. But this was towards the end of my postdoc time. We were trying different ideas and so on. So this is like what we are trying to achieve. That's our startup logo. And basically, we are trying to develop a high-precision cell-based diagnostic system to help clinicians like make fast, affordable, and informed decisions for cancer diagnostics. That's the vision. The team is like kind of so much fun to work with them. It's a dream team, we call. Basically, Uğur, he's the chemical and biomedical engineer and has his PhD from the ETH Zurich. There is the Erdost. He has actually a trained medical doctor from Hacettepe University and did a neuroscience PhD at the Koç University. And now he's in Max Planck Institute for his postdoc merit fellowship. And you met with me, and we have the fourth member starting in August. She has a PhD in cell therapy, so perfect fit. And right now she's doing the MBA, wrapping up her MBA. So basically she will take more on the business application and application fit side. But the best part is she also understands the technology in depth, so that she can talk to the clinicians, etc., in detail and understand their problems and basically make our platform better over the time. It's a kind of a cliche, but this is where we are right now, the body of that. This is the pre-startup phase. We are not commercial yet. We are still under the big arms of different institutes with the public funds. And we try to basically find some money, some funding, and then develop the technology. And then after developing to a certain point, we try to find bigger funding to move on this valid that. And I would say we are right now here, but you never know. You will see at the end, if you can pass it where you were at a time. But I think we are somewhere here, and we need to cross this valley of that. It's called this because it's not interesting for public funds to fund you. You cannot publish good papers. It's also not interesting for the private funds because you cannot really bring money at the point. It's high risk. So you need to cross it. And right now, what we have is different funds through like small organizations. One is through Max Planck, which is called the Max Planck Innovation. This was only for the checking the market if there is a really need there. And right now, our main funding comes from Stiftung through Cyber Valley, which we got like last year, and we applied for the next one right now for the next year. Let's see what will happen. Cross fingers, and we already have several letter of intents, and we are trying to actually right now finalize 3 agreements with 2 places from Tübingen and 1 from Heidelberg. These are close by cities famous for their clinics and so on. And we will try to basically get samples from them and try our device and send our device also they can test it later. And our current setting is a bit weird. That's also why you've seen a lot of logos. We are somewhere in between. We are located at here. The money comes from here, but the funding was organized by Cyber Valley. So it's kind of all together at the same place. And if you are curious about our journey, please follow us on LinkedIn. You can also find it if you just search for Salon Roll. And I'd like to thank you all for listening to me. And if you have any questions, please shoot it.